Shumakai Chaudhary, and welcome to IUCAA's Thursday Colloquium. I'm glad people still remember when Thursdays are and turn up at 4 p.m. I'm glad to see a good turnout for today's Colloquium. We went online about 3 months ago, and a lot of you have been with us. I see a lot of new names today in the audience, which shows that having a large spread of subjects attracts a wider audience. Thank you for coming. I'm very, very happy today that in our normal colloquium series, we always showcase the work that is done by our members of faculty. And today we have one of the members of our core faculty, Dr. Subhadeep, who will talk about his work on optical atomic clocks. And Subhadeep did his PhD at the University of Groningen, and then went and did some postdoctoral work at the National Institute of Standards, NIST in the US, with joint Quantum Institute of NIST and the University of Maryland, and then came back to India and joined the National Physical Laboratory in New Delhi and did some great work with the atomic clocks there, which he's going to, I'm sure, talk about. And then joined IUCAA recently, at the end of last year, as part of our core faculty. And I'll hand you over to Subhadeep, but we'll tell you that at the end, what we'll do is we'll take questions from within the Zoom broadcast. This is also being broadcast in webcast on YouTube Live. But those of you who are in Zoom, if you want to ask questions, go to the participants window and raise your hand at the end. Now we are disabling that. And you can raise your hand, and then I'll ask you to ask questions one by one. And from the YouTube broadcast, if you type in your questions in the chat box, we will gather some of those questions and present it to the speaker towards the end. Let me hand you to Subhadeep.
Thank you, Professor Chaudhary, for the kind introduction, and good afternoon to everyone who have joined.
Subhadeep, your sound, you have to adjust your sound. It's not coming very well. Thanks.
Hello. Is it? Am I audible?
Better. It's better.
Yeah. Thanks for the kind introduction, and good afternoon to everyone who have joined today for this talk. So, as you see in the bottom of the slide, those who are familiar with the IUCAA, you know that already. This is the nice Pune area of our institute, and on the top you see the sundial, which is at the science park of IUCAA. And today, actually, I'm going to talk about slightly better clock than the sundials. These are called optical atomic clocks. These are atomic clocks in the optical domain. And particularly, I should focus on how these clocks can be used to probe the fundamental science, because that is as a physicist, that is our main motivation. So let me begin my talk. Whenever we are talking about the fundamental science, the first things comes in our mind are fundamental particles as well as the fundamental force. So here you see, like, to best of our knowledge so far, we know there are 4 kinds of fundamental forces. As you see in this slide, this is like strong force, electromagnetic force, weak force, and the gravitational force. The strong force, which keeps the quarks together, this is the quark-gluon interaction plasma, and the carrier for this force are the gluon or pions. For the electromagnetic force, it works infinitely, basically from the electron to proton distance to infinite, and the carrier of this interaction is photon, which is another boson. For the weak force, this is responsible for radioactive decay. Neutron and proton, they exchange W bosons, and these interactions happen at the nuclear level at 10 to the minus 18 meter level. The fourth one is, of course, the why apple falls towards the earth, that's the gravity. Okay. Now, for all these forces, there has to be a boson which is carrier of these interactions. As you see, for the strong electromagnetic and weak force, we know what are the bosons like pion or photon or W or Z bosons. But there are many open questions in this fundamental aspect of the physics. Like, I mean, we expect that there should be a graviton for the gravitational force, but it's not still detected yet. And also the other most important thing, I mean, there are many open questions in this fundamental understanding, and that's the reason why we have to study fundamental physics, to understand these things better and better. For example, like why there is only 4 forces, why there is not a 5th force. Yeah, why there are like let's say 6 type of quarks, why there is not a left-like quark. Similarly, this kind of questions. The one more important question is like the strong force, electromagnetic force, or the weak force, they can be explained through quantum mechanics like quantum electrodynamics or quantum chromodynamics or quantum flavor dynamics. However, the gravity actually still maintains a social distance from that. It's not yet explained by the quantum mechanics, and it's an open question. So for the remaining 3 forces like strong force, electromagnetic force, or weak force, it can be coupled all together and by a single theory called standard model, which can explain all this theory of particle physics of these kind of 3 forces. But the gravitational force is not yet included into the standard model. So there are many such kind of open aims of our understanding so far, and those tells us that we need to study more and more from, we have to make different kind of models, and we have to test those models through the physics experiment, and they have to be together. Yeah, I mean, if you have some model which there is no test, maybe not at this moment, but it could come in the future. For example, let's say string theory. But it's important to develop this kind of new ideas and new model, and then maybe at some point some experiment will come which will ensure that this model really exists, and etc. So there are different kind of experiments. I am talking about the experimental part today. So there are different kind of experiments. One kind is like big experiments, like mega science experiment, which involves lot of people, like let's say thousands or maybe few thousand people all over the world in different parts of the world, and they contribute together to understand these things. For example, as you see, the most important thing is looking into the sky through the electromagnetic spectrum or through the gravitational wave using different kind of detectors like radio frequency detectors or optical detectors or X-ray detectors or gravitational wave detectors. This is one way of doing this fundamental physics. It could be done through the high energy physics side. For example, this is what you see the picture of Fermilab, the G-2 experiment, why G is not exactly equal to 2, but slightly away from 2. This anomaly people are trying to find out through different kind of experiment, particularly like muonic experiment and etc. etc. LHC is another example where people are trying to make new particles, trying to accelerate the particle, then high energy physics experiment again. Detecting the neutrinos is another thing, like a super Kamiokande neutrino detector in Japan. These are only few examples. I just want to show you that this kind of experiments works, which involves many people, not like it's not a small experiment. It requires skill from different aspects of the field, from technology to physics to engineering to many things, and they have to come together and do this kind of experiment. On the other hand, there are different kinds of experiment, which is a tabletop experiment. For example, it's a small, like let's say sizable small group, 10 people maybe, or on that order, and they do very precise experiments, and they also test the fundamental aspects of the physics. And many cases, these experiments are based on atomic molecular optical physics, like the atom-photon interactions and etc. So here, as you see, some example of the tabletop AMO experiment, like the first one, you see the parity violating beta decay experiment. This is what you see here, this small dot. This is actually trapped sodium atoms. It's about 1 billion sodium atoms trapped in a magneto-optical trap. And this is sodium-23, which decays to the nuclear decay by beta decay. And the actually the mixing between electromagnetic and weak interactions, it's called the Weinberg angle, that can be measured in this kind of experiment. And as you see, I mean, this is a low energy physics experiment. Like the atoms are cooled to millikelvin temperature, like almost to the 0° Kelvin, which is completely in a different regime compared to the high energy physics experiment where the particles are at TeV energy range and so on. The other one is like measuring the permanent electric dipole moment of atom. The atom should not have any permanent electric dipole moment to our best of our knowledge, because if there is an electric dipole moment, it violates different kind of fundamental symmetries like time reversal symmetry or parity symmetry or CP, and in that sense CPT also, which are actually good symmetries in our known standard model. So if there is any electric dipole moment of an atom, of a neutral atom, then it violates these fundamental symmetries. That means we have to understand the physics differently. We have to understand our standard model differently. So theoretically, it's predicted that there could be some electric dipole moment, but so far, through different kind of precision experiments, we do not know what it is or whether it really exists. Just to give you an example, like about 40 years ago, the theoretical prediction of electric dipole moment was 10 to the power minus 17 or 18 electron centimeters. So far, since then, in last 40, 50 years, the experimental sensitivity has reached to 10 to the power minus 31 electron centimeter by Edhines group in UK. And they measured the electric dipole, tried to measure the electric dipole moment of electron, but still it's a null experiment. There is no absolute value of the electric dipole moment, and theory actually gets upgraded. Once we know this experiment, do the experiment, we understand, and then theoretical things, understanding also gets upgraded and upgraded. That's how it works. Another experiment what you see is the parity violating experiments in radium ion in UCSB, USA. It's also like all these experiments are actually using very ultra cold sample of atoms. The atoms are almost at the 0° Kelvin, or almost they have no energy. The last one, what you see is atomic clocks, what I'm going to talk about today, and these are optical atomic clocks. They can be realized in two different ways. I will come to that point. So these are again a few examples of the tabletop experiment, which again gives you the fundamental science. You can taste the fundamental science using this kind of tabletop experiments and in the low energy sectors. So now actually the world is going far beyond this kind of tabletop experiment. Now people have realized by having a small tabletop experiment, you can reach to a certain level of accuracy, which is very good accuracy, but not yet all the fundamental physics can be understood or can be probed. So what they are doing, they are actually networking this kind of tabletop experiments. So there are some like fiber networks and etc. And they are connecting all these different experiments which are spread over the world together. And here, as you see, this is actually true for many different sectors. It's not only for the atomic physics sectors. This is some examples where networking of the experiments work. Like here is the first networking, to best of my knowledge, came actually through this connecting the different cesium clocks throughout the world, which maintains the international level of SI seconds. So this is like about 330 cesium clocks over different parts of the world, including India. They are contributing to the BIPM in France and maintaining the SI seconds. Here you see the different kind of radio telescopes in the world. They are connected. It's VLBI. Then next generation, the Event Horizon telescopes. Some radio telescopes, they are connected. These are different gravitational wave detectors throughout different parts of the world. They are connected together and they're looking into the sky at the same time and trying to detect the gravitational waves. And similarly, the different optical clocks in different parts of the world, as you see these red dots, which shows the position of these optical clocks. And here, within the zoomed up area, you see the optical clocks in European Union countries, and this is in China. Just to give you an example, the similar thing also exists in Japan as well as in USA. So they are getting connected together. Even it's going beyond the national levels, going to the intercontinental level, and they are getting connected together to enhance their sensitivity or enhance their capability to measure the fundamental science. So if you look over last 100 years, what I basically told you so far, like approximately 100 years ago, the quantum mechanics was formulated. And since then, physics or our knowledge in science has improved significantly. Like for example, we understood different kind of quantum effects in the special theory of relativity, general theory of relativity were formulated, different kind of quantum field theory was formulated like QED, QCD, QFD, and together the standard model. Many important inventions were made. Few examples are like Higgs bosons, black hole, gravitational wave, etc. And at this moment, in let's say last few years, and it will be remaining for another few decades, we are actually going through the second quantum revolution. So now we are in an era of using this quantum effect or to use our quantum mechanics knowledge to make devices, to use them in our regular life. For example, is the quantum communication and quantum computer. So these slowly we have been realizing in the world, like how to use these quantum effects in our daily life, quantum information processing. So as our scientific knowledge becomes better and better, we also realize the importance of the clocks. And the clocks in last 100 years have developed from mechanical pendulum clocks to the optical clock. And here you see in this figure, the accuracies of the clocks, how it has improved. And this is like this pendulum clock, which is about 100 years ago from now, it had an accuracy of few seconds over 1 year. And today, the best clocks, optical clocks, have an accuracy of few seconds over 34 billion years. So let me repeat, 34 billion years and only 1 second in accuracy. Whereas the universe has an age of 13.88 billion years. So that means if supposedly there was a clock which was running since the beginning of the universe, it would have not lost a single second so far. That's the kind of accuracy what we are talking about today. And these kind of clocks are actually used to probe the fundamental science, not the simple clocks. And if you see what kind of development has happened technically and also different kind of instruments, it basically starts with during the time of Second World War. Rabi is the pioneering a person of that activity. He is actually pioneer of the present, let's say, atomic physics activities. And he first came up with the idea of atomic clocks. I mean, the atoms can be used to measure the transitions and can be used for a clock. And we know that he developed this atomic beam magnetic resonance technique. For that, he got the Nobel Prize. And we also know about the Rabi spectroscopy and etc. Then it was further improved, that technology was further improved by his PhD student Ramsey. And the spectroscopic technique is known as Ramsey spectroscopy. Soon after that, cesium clock was actually realized using the spectroscopic techniques, which was developed by Rabi and Ramsey, and it was commercialized very soon after that. Like in 1955, first it was realized, and in just 3 years it was commercialized, initially by Hewlett-Packard company. And still actually it's the same technique what we are doing for our regular purpose of clocks. And depending on that clock technology, that atomic clock technology, which is a cesium beam clock, the SI second, SI is International Standard of Unit, which is maintained by an international community situated in France, in Paris particularly. The name of the organization is called PIPM, and India is also part of that. They redefined the second with respect to the atomic clock. Earlier, it was based on rotation of the Earth. We know GMT and etc. Then it was changed from GMT to atomic clock-based definition in 1967. Later on, several important technologies were developed. Like one of them is laser cooling and trapping, which brings the atoms or cools the atom to almost 0 degree Kelvin. That was also Nobel Prize winning thing. And implementing that to the earlier technology, then cesium fountain clock was realized, which uses the ultra cold sample of cesium atoms rather than just normal cesium atoms at room temperature or slightly above room temperature. As a result of that, accuracy of the clocks improved by several orders of magnitude. And then in 1999, it was the SI second there was an amendment, not redefined, was amendment of the SI second. And in 2001, first optical clock was realized. So far, the cesium clocks are actually in the microwave clocks. They work in the microwave domain. The frequency is 9.2 gigahertz, whereas the optical frequencies are in 10 to the power 15 hertz, few hundreds of terahertz. If you go to higher and higher frequency, your clock accuracy increases because the clock accuracy is inversely proportional to the interrogating frequency. So as the frequency increases by, let's say, 3 to 4 orders of magnitude, the accuracy also improves by almost similar factor, not exactly, but almost similar factor. And there are two types of optical clocks were realized. That is the optical lattice clock and optical trapped ion clock. I will come to that in a few minutes. And since then, many things, I mean, so far, as I said, that most accurate clocks have an accuracy of 1 second, let's say inaccuracy of 1 second over 30 billion years or 34 billion years, and etc. And in next couple of years, in 2016 approximately, we actually expect a second redefinition of second based on these optical clocks. Okay, once I said about these different kind of techniques and technology, you'll be surprised to see that altogether 10 Nobel Prizes are awarded in all these kind of technologies so far, starting from Rabi, and then further spectroscopic techniques were developed by Swallow, and then Rabi student Ramsey got due to the Ramsey spectroscopy. Then Demelt and Paul, they were inventing the ion trapping techniques, which today we use for making the optical clocks. Then these three gentlemen, Bill Phillips, Cohen Tanuji, and Steve Chu, they were inventing the laser cooling technology, and they were awarded Nobel Prize in '97. In 2005, Kate Hanch got Nobel Prize because he was inventing one of the very important tool, which is called frequency comb, optical frequency comb, which is actually an optical frequency counter, which is one of the key components for an optical clock. And in 2012, Dave Wineland got Nobel Prize because for pioneering work on trapped ions and quantum entanglements and etc., which is nowadays used in a trapped ion clocks and etc. So you can see that how important is that, like all these technologies were slowly developed in last, let's say, around 80 years or so. And in the last 8 years, 10 Nobel Prizes are awarded in different kind of technologies, which are being used in present day state-of-the-art atomic clocks. So that gives you an idea what kind of state-of-the-art level of that atomic clock technologies they actually use it. And as you see here, like this is the since 1967, how the SI second got improved. So in around that in 1960s, 70s, and up to 90s, the SI second were accurate to, like, let's say, few nanoseconds, which has improved to picosecond order at present, and that is because of this laser cooling technology. So atoms are able to cool to almost microkelvin temperature, which is, let's say, almost very close to the 0 degree Kelvin temperature. And as a result of that, many kind of systematic effects which plays important role for this accuracy were almost eliminated, or almost like got down to very close to zero, were neglected basically. And that was the reason that the accuracy of this kind of clocks, or this is still actually microwave clocks, they were improved by 2 to 3 orders of magnitude. And these are like from cesium beam clock, where this one, to laser cooled cesium clocks, which are used today here in the microwave domain. And the present days, the fractional accuracy of this kind of microwave clocks are on the order of 10 to the power minus 16. So fractional accuracy means the line width of the measurement divided by the frequency, delta nu over nu zero. So today what we are going to use, or what we are going to emphasize, that is the optical clock. This is in the optical domain. And the optical clocks are realized in two different ways. This is the trapped ion, this is a schematic picture of the trapped ion clocks. So this is the ion trap. These are different electrodes where a single ion is trapped here in an oscillating potential like that. What you see, this is an oscillating potential. This is created by applying proper radio frequency electric field to these electrodes. And that's why a single ion can be trapped or confined at the center, and then further they can be laser cooled to almost 0 degree Kelvin temperature by using different kind of lasers. The another way is you can create a artificial lattice. It's called optical lattice. So you can use a counter propagating laser beams, and if they're in right phase and in right intensity, they will interfere. These counter propagating laser beams will interfere together and will create a standing wave, a periodic potential. And at the nodes or antinodes of this potential, this is the potential minimum. In a 2D, it looks like this. You can imagine it like an egg carton, and the eggs are like atoms which are stored there. This is an easy way to imagine that, and that is created using lasers. And there also the atoms are laser cooled to millikelvin temperature. So the difference between ion trap and atom trap is in case of neutral atoms, you can use thousands of atoms because they basically don't have any Coulomb interaction type of thing, even though they have a main field interaction. This is collisional shift and etc. So the disadvantage of neutral atom optical lattice clock is they have a collisional shift which shifts the actual clock frequency. Whereas for the single trapped ion, in this case, you have to trap only one ion. The reason is ions have a ions are charged particles, so they will have a Coulomb repulsion. If you have multiple ions, then they will have a Coulomb repulsion, and this Coulomb repulsion will shift the clock frequency. That will perturb the clock frequency, which is not good because we have to measure that clock frequency as much accurately as possible. So for ions, you can use only one ion. So as a result of one ion, your signal goes down, but you gain because you don't have any collisions. Your collisional shifts are zero, and you have a very long time of coherence. Because if you have multiple atoms or multiple ions, then they can be decoherent very quickly. If you have only single particle, then they can be coherent basically for almost infinitely. So you have a very long interrogation time. So you gain by that. You can interrogate the ion for very, very long time. So these are the two ways how you can realize the optical clocks. And what you basically do once you produce these trapped atoms or trapped ions, you drive the clock transition. This is a particular type of transition which has a very ultra narrow frequency line width. So this delta nu is very, very small. It's on the order of, let's say, nanohertz to millihertz. Typically for an electric dipole transition, delta nu is on the order of few tens of megahertz. But if you have delta nu is tens of megahertz, you cannot make a very good clock because you are limited by the line width of the transition. So you can measure hundreds of terahertz with an accuracy of, let's say, few tens of megahertz, which is not a very good clock. So you have to select a particular transition which we call highly forbidden transition. So it's not an electric dipole transition, but it's an electric quadrupole transition or electric octopole transition or something like that, hyperfine induced transitions, which are very hard to drive. It's not easy to drive. But the line width of these transitions are on the order of millihertz to nanohertz. So that means you can measure 10 to the power 15 hertz with an accuracy of, let's say, tens of millihertz or something like that. Yeah, so far using these techniques, people are able to create clocks with an accuracy of fractional accuracy of 10 to the power minus 19, and still we are feeling that it's not yet there to actually measure some. I mean, we can do a lot of things using that. We can measure a lot of physics with that, but not all. So this is the present scenario, or let's say scenarios how the atomic clock accuracies has increased in last several years. These blue and green ones are the microwave clocks, and these yellow and cyan dots are the optical clocks. So this yellow is the trapped ion clock accuracy, which has reached to an accuracy of 9.4 10 to the minus 19 in aluminum ion clock at NIST in USA. And this is the accuracy of strontium lattice clock, which has reached to an accuracy of 2.5 10 to the minus 19, again at NIST USA. And these were realized almost within a gap of few months. What kind of physics or fundamental science can be done using this kind of very, very accurate clocks? Here I have listed few of them, like we can measure constancy of the fundamental constants or constancy of the fundamental symmetries, which have been explained very well in our known standard model. So if it is found that it is not constant, that means we have to improve our knowledge on the standard model. It could be used for geodetic measurement. Even there are proposals that it can be used to measure the to search for the dark matter and etc. But it requires more accurate clock than what we have at this moment. There are proposals that it could be used for gravitational wave detections also, and most importantly, it can be used. I mean, it is used actually in this case for quantum information processing, quantum communication, and quantum entanglement, this kind of things. Also, it's very much used for radio astronomy also. So today, I won't have time to go into all of these things, but I picked up 3 of these fundamental physics studies that can be done, which we are actually interested and plan to do at IUCAA in future once the optical atomic clock is developed here. And that is looking into temporal constancy of fine structure constant, searching for possible or not possible violations of Lorentz invariance, and geodetic measurements. So let me begin with the variation of the fine structure constant. So this idea first came in 1967 by these 2 gentlemen, Buckle and Smith in Caltech. So they published a 1-page PRL paper. This is a 1-page PRL paper, and the title of the paper is "Does the Fine Structure Constant Vary with Cosmic Time?" And they suggested that it can, I mean, they actually gave some numerics, some quantitative analysis, that it can be measured by measuring the fine structure splitting in astronomical spectra. And they gave the number that if there is a variation of the fine structure constant, it's below 3 times 10 to the power minus 3 over 2 giga-year. And if you put these numbers together, it's approximately 1.5 times 10 to the minus 12 per year. After that, in 1999, so it's like almost 33 years later, the Australian group, a theoretical group in University of New South Wales, they proposed it can be done better by measuring the quasar absorption spectra. And soon after that, their colleagues, experimental colleagues from the same university, they actually gave the numbers by some quasar absorption spectra analysis. And since then, actually different kind of experiments have been tried out to measure the variations of delta alpha, or relative variation of delta alpha by alpha. One of them is, of course, what I'm going to talk about today, that is by measuring the clock comparisons. And these are few experiments which have been carried out by different groups in the world, and the typical numbers are, let's say, few times 10 to the power minus 17 on that order. Our Indian colleagues, actually from our own institute IUCAA and from our neighboring institutes from NCRA, they are pioneering to measure the redshift of quasar absorption spectra and derive the quantities of delta alpha by alpha. This is last year paper, 2 years before, Nissim Kanekar, who gave this value by measuring the radio frequency spectrum of the quasar lines. And this is Professor Srianand from our own institute. He came up with this value 10 to the minus 16 few years back into the optical domain. There are also measurements. There is a natural nuclear reactor in Gabon. Gabon is a city in Africa. It's called Oklo Natural Uranium Reactor. And by looking into, like, I mean, if you measure the uranium-235 to uranium-233, there are 2 isotopes, the ratio of them, there is a mismatch between this ratio to whatever you can get in any terrestrial objects and etc. And from that, they use the right nuclear models or decay models. And they said, I mean, this nuclear reactor is actually running for billions of years. I mean, maybe few billions of years since the very beginning of the Earth or something like that. And in this model, there is a quantity alpha. And if you can match with this ratio of uranium isotopes only if alpha is varying to some extent and etc. But the point is, if there is any variation, this is so small that we are not able to measure it so far. We can only give some sensitivity of our experiment for all these experiments. There are also measurements tried out by looking into a microwave transitions in dysphorium atom. There is a very sensitive, alpha sensitive microwave transition in dysphorium atom, and this has been measured very accurately by a few groups, and they try to give some numbers of the alpha variations. There are also proposals in different ways to measure these things, these alpha variations. But now actually what world is going to, they are going to network different kind of experiments. This is, for example, networking of different kind of UV telescopes. And the recent result, just a few years, this is the last year result, it came up like next generation high resolution spectrograph from different kind of UV telescopes. And this is also networking of different kind of telescopes, which gave better result compared to using the spectra detected by a single telescope. Similarly, for the atomic clocks also, as I said, the networking is coming up. So the atomic clocks are being networked together. For example, as you see here, this is an European Union network. This PTB is in Germany. The NPL is in UK, and CRC is in Paris. So the network, they are networked using the optical single mode optical fiber and ultra stabilized fiber. It's not, I will come to that point. This is not just a simple optical communication. These fibers are ultra stabilized fiber, and these clocks, optical clocks in 3 different countries, which are separated by, like, say, about thousands of kilometers, they are connected together, and these optical clocks are being compared. And it's expected that much better results, at least 2 orders of magnitude better results, will probably be coming up for this alpha variation measurement. So let us try to understand why alpha should vary actually. I mean, there are many different kind of theories, starting from, let's say, simple theoretical model to very hardcore theoretical models. I won't go to the very hardcore theoretical models which are derived from, let's say, dark matter and etc. etc. But let us try to understand in a simple way, why do you think that alpha should vary to our, let's say, general knowledge what we have. So the value of alpha, what so far has been measured and given to the core data, is 137. This is the, by the way, the alpha for the electromagnetic interaction. So this is a fine structure constant for the electromagnetic interaction. So we know that value is 1 over 137, but it's actually not exactly 1 over 137, but it's actually 137.03999.084, which is measured up to like 9th decimal point. Yeah, this is measured so accurately. Now, if there is any variation, it's actually variation at that point, what we are, different people or different experiments are trying to measure. So you can write the alpha in SI unit like that, square by 4 pi epsilon 0, and this has a dimension of energy times distance, but the entire quantity alpha is dimensionless because it's divided by 1 over h bar times c. C is the velocity of light. This h bar by c also has an unit of energy times distance. So then it makes the entire quantity alpha dimensionless. Now this is for the electromagnetic interaction. So that means an electron which has a spin. So if the charged particle has a spin, it should have a magnetic flux. And let me define a quantity phi 0, which is actually quantized magnetic flux from a spinning of electron. So then I'm deriving 2 different quantities which I'll use for my next, let's say, description. Phi m is nothing but phi 0 square by 2 times mu 0. Mu 0 is permeability. And phi e is electric flux because it's a charged particle, so it should also have a quantized electric flux, and that is E square over epsilon naught. Now, if I take this part, 1 over h bar times, let's say h bar times c, and that I can write in terms of this phi e and phi m, like this, square root of 2 by pi, square root of phi e times phi m. If I take a relative derivative of this quantity, then you will get some constant times delta phi e by phi e plus delta phi m by phi m. Once I do the same things for the other part, epsilon, e square by 4 pi epsilon naught, we can also write this entire alpha in terms of square root of phi e by phi m. And then if I take a relative derivative of alpha, then I can get another constant, which is different than this constant. but here I get a negative sign. So here this was a positive sign, there I get a negative sign. So if I make this part 0, if I consider h bar c is a constant, really constant, so that means this quantity has to be 0. If I take this is as a 0, then I get this relation, and if I use this relation here, then delta alpha by alpha is non-zero. Right? Now this relation is more or less I would excuse me. If the total electromagnetic energy is conserved, so that means your total electric flux and magnetic flux are not changing, the sum of it may like interchange, but the total quantity should not change. That means this quantity, this with the plus sign, that has to be 0, right? If I take the total electromagnetic energy is conserved, then I will come out with delta alpha by alpha is varying. On the other hand, if I take delta alpha by alpha is 0, then my total electromagnetic energy is non-conserved, which is not our standard model physics. Like we know that total energy is conserved. So where this energy is coming? Then there are different models, like maybe some other form of energy gets converted to the electromagnetic energy, and so on, so on. So anyhow, the point is we have to find out whether alpha is really conserved or not. Then we can only go to a conclusion, okay, the total electromagnetic energy is not conserved or whatever, etc., etc. So as I said, that thing can be measured by very accurate measurement of the electronic transitions in the atom in the optical domain. So any energy level, atomic energy level, we know that from Bohr's theory, Sommerfeld theory, and Pauli's correction, and so on, we have read it in our childhood. It can be approximately, let's say, written like that. The first quantity is the non-relativistic part, that's the simple part. Then this part is actually finite size of the nucleus has a finite size, so that correction gives some small correction factor to this one. And the middle part is the relativistic part, that is proportional, that is, it depends on alpha, fine structure constant, and that also gives a slight corrections to this non-relativistic contribution of the energy level. So if I just put some numbers, this is for a typical case, it changes case to case, I mean from species to species. So maximum contribution actually comes from this non-relativistic contribution, that is, let's say 99%, or it could be even more. A small correction comes from the nuclear finite size, by the way, this scale is logarithmic scale, and also a very small correction comes due to the relativistic part, and which is alpha dependent. And for different atoms, this alpha dependency is also different. So anyhow, for our purpose here, we can write in, let's say, the energy difference between two states of an atom. If you consider the bottom state is a ground state at zero energy level, then the excited state energy is basically delta E. Or if you consider they are at two different excited states, then the energy level difference is delta E, and which is equals to Planck's constant times W clock. W clock is the clock frequency or frequency of this transition. Then delta E can be written like W clock times Planck's constant, which we can simply write as R alpha times CH. This is unit of energy. R alpha is the Rydberg constant and a function of alpha. Yeah, it could be function of alpha square plus alpha to the power 4 and so on. Just let's consider this is just some dimensionless quantity which is function of alpha. If I take relative derivative of that, then simply I can write this delta W clock divided by W clock is with some sensitivity factor times delta alpha by alpha. And this sensitivity factor is different for different kind of species, different atoms, because that is alpha dependent and which depends on energy level structure of a particular atom, which is different for different type of atoms. So if you select a let's say potential candidate of atoms where the sensitivity is much higher, then you have a better chance to measure these alpha variations. And this is what calculated for few good species, ionic species and atomic species, which are used for clock purpose. For example, this is aluminum ion, strontium ion, indium ion, ytterbium ion. Ytterbium ion has 2 clock transitions, and some neutral atoms like calcium, strontium, ytterbium, and mercury. All these species are used for to build optical clocks, and they have different kind of sensitivity. Out of them, you see that ytterbium ion octopole transition, this is S to F transition, which is very, very hard to drive, like highly, highly forbidden transition, which is used to measure, to build one of the best clock in the world that has the highest sensitivity. Forget about this sign in front of it. So this has the highest sensitivity compared to any other species, and aluminum and similarly like strontium neutral atoms, they have the lowest sensitivity. That means if you measure the clock transition over a long period of time, let's say you do it for strontium atom, then the clock frequency won't change that much because they have the least sensitivity. And if you do it for the ytterbium ion octopole transition, then it will change quite a bit because it has the highest sensitivity. So if you make a clock comparison between strontium atom and ytterbium ion clock, you will have a very good chance to measure whether alpha is actually varying or not varying. And so these kind of experiments have been done, and the reported results I already showed you few slides earlier, like they have reached to a sensitivity of 10 to the power minus 17 per year. So if you see, like in last, let's say 15 years, since 1919, the first result came from the quasar absorption spectra, and the last optical atomic clock comparison results in 2014, the sensitivity has improved by almost 30 times. So on an average factor of 2 per year. But yet there is no, I mean, all experiments are null results. So it's only experimental sensitivity, but there is no value of actually alpha variation and etc. But it's very important to carry out this kind of experiment. In fact, different kind of experiment to find out whether actually alpha is varying or not, because this gives answer to many of the unanswered questions like whether dark matter exists and etc. Because these models are actually connected to why alpha should vary, or quantum nature of the vacuum is breaking into electron positron pair and recombining, or some ghost quantum field which may violate equivalence principle or not, etc. Anyhow, the point is, like, if you want to have a grand unification of the standard model, including the gravity, or you want to start the, we want to know the present standard model in a much better way. That means to unknown questions of unanswered questions of the standard model. Then we have to carry out this kind of experiments. These only can give the answers. So now let me go to the second experiment, that is looking into local Lorentz invariance violation. So this Lorentz invariance was first proposed by Einstein, I think in 1905, and then Lorentz was the first person to make the mathematics of it, Lorentz transformation. So which says basically, like, if there is any measurement, if you do any measurement in a standing frame, I mean, basically it says that the measurement or any physics law should not change by different orientation of the reference frame. So it's a reference frame independent. Laws of physics are independent of the orientation of the reference frame. That's what it means. Now, if it violates, what will happen? If it violates, if you, let's say, measure some quantity in a moving frame and compare it with a stationary frame, they should give a different value because the Lorentz invariance violates. Or if you measure same quantity in two different frames which are moving differently, then also it should violate. It should give these different results. So anyhow, the point is, if there is any violation of the Lorentz symmetry, then it also violates CPT. CPT means charge conjugation parity time reversal. This is a very good symmetry to known as in the standard model. So if there is any violation of the Lorentz invariance, it also violates the CPT symmetry, and that means it's beyond the standard model. We have to understand it in a different way. So what can be done using the optical atomic clock? So just to give you an idea, this is, let's say, this is the cosmic microwave background as it is measured by different kind of detectors over several years. You see it in different resolutions, etc. It's considered to be as the rest frame of our universe. Yeah. Now, our Earth which is moving, which is rotating around its own axis, and also it's rotating around the surrounding the sun. So that means it's a rotating frame compared to the rest frame like the cosmic microwave background. So if you have a clock on the Earth, that means once it is rotating, with respect to the rest frame, it's changing its orientation. Yeah, but how to measure that? Because your measurement is also in the same reference frame, right? So your measurement as well as your the experiment from where you want to measure, they are in the same frame. So both of them change. So you cannot really do this measurement in this way. So what you have to do, you have to have multiple clocks which are oriented differently. And the orientation of the clock with respect to the reference frame, that is connected by a tensor. It's called C mu nu. It's a second order tensor, which gives you the coupling between the one frame to the other frame. In this case, the Earth frame or the laboratory frame to the rest frame, that is the CMB frame. And if there is any violation of the Lorentz symmetry, then the perturbation in the clock frequency or the perturbation between two states which is connecting this clock transition is correspondingly this one, like 1/6 C0. C is this tensor, and T depends on the atomic properties. So for a particular atom, for a particular atomic structure, T is a particular quantity. So it's different for different atoms. So the experiment is following. Here, these are not the Schrodinger cats, like not the dead or alive cat. In this case, these cats are actually the clocks. And why did I choose cats? Because they have a pendulum like their tails, and they are oriented differently. This is only to give you the impression, nothing else. So in this case, these two clocks, they are oriented differently. So their pendulums, one is along the gravity, and other is, let's say, in some other arbitrary direction compared to the gravity. And they have this C tensor element differently because they are coupled. Since their directions are different, their coupling to the rest frame, like the cosmic microwave background frame, that should be also different. So there is like two different C parameters for two different clocks, and their difference, this C mu nu 1 minus C mu nu 2, that quantity over the time should change because both of them are changing differently. They are not changing in the same proportional. They are changing differently. Yeah. So if you measure basically this change of difference, then you have a chance to measure whether Lorentz invariance is violating or not. And that experiment have been done in PTB, Germany. So this is from their paper. So they have it will be two different ytterbium clocks, ytterbium octopole transition clocks, and they have oriented these two different clocks in two different directions. As you see, this B, direction of B, this is basically quantization axis by applying some magnetic field. That's why it's B, and they are oriented differently, which are just situated. Both of these clocks are situated next to each other. Both of these clocks have almost identical in nature except the orientations. All the systematics are very accurately derived. So they are very, very ultra precise, ultra accurate clocks. Only the difference is their orientation. And as the the Earth rotates around its own axis or surrounding to the sun, this relative orientation with respect to the CMB also changes, right? And how this changes the clock frequency is following. This is the quantity, that's how it changes. And why ytterbium? Because ytterbium has the highest sensitivity again for measuring Lorentz invariance violation as theoretically predicted. And the results are following. So they try to extract these C mu nu tensors, which actually says what is the variation. And as you see that these are about few orders of magnitude higher compared to the astrophysical limit or any other experiment. They have compared for 4 different, this is their own experiment, and this is a calcium ion experiment. This is looking into dysphorium ions microwave transition, and this is from the astrophysics experiment like quasar absorption spectra. And you see that this is at least few orders of magnitude better. This atomic clock comparison is few orders of magnitude better compared to the astrophysics experiment. See, the main difference here is for the astrophysics experiments are very nice. The problem is the resolution. the spectrograph resolution that one can achieve is not as accurate as one can achieve the accuracy in an optical clock. And day by day, both of these things are improving. So maybe on one day, both of them will exactly match with each other. So a much better experiment could be, which is planned for the future, like putting optical clocks in different parts of the world, as well as in International Space Station and different satellites, yeah, which are surrounding around our Earth. But that actually requires to develop very small, compact optical clock. Now the optical clock which have been developed, it's like a full laboratory, let's say sizable laboratory with lot of optics, lot of electronics, 2 or 3 optics table with full of things and etc. That cannot be put into a satellite. Yeah, so you have to make everything, you have to miniaturize everything, starting from electronics to your ion trap to your laser systems and etc. And one important thing is miniaturizing of the ion trap itself, because the typical, let's say at this moment, the trap size is 10 centimeters. I mean, not only the trap, but trap together with the holder and etc. etc. If you can bring it down to few millimeters, then the power consumption will be much less, then the total size of the entire system will be much reduced, and then one can think of putting everything in a box and putting it in a payload and etc. etc. So the ion trap actually have been miniaturized by few of the groups in the world, and it's important not only for the clock purpose, but also for the trapped ion quantum computer. So it has multiple applications. So it's very important to develop this kind of chip level ion trap systems, which has applications for the small clocks as well as for the trapped ion quantum computer, which is very important to develop for any developed countries or countries who wants to develop, like India also, it's very important. So now I'm going to the last or third application, that is the geodetic measurements. And the geodetic measurements are like basically measuring the geometric shape of the Earth or orientation of the Earth, which changes a little bit, or change of gravitational field from the at different heights from the Earth. So here what you see is very small portion of Earth, what I'm trying to show, and this blue one is the sea level. The green is basically the surface, Earth's surface. So wherever it is below the sea level, that means you have there an ocean. And the important part is what we are going to discuss now, that is this magenta one, that is the geode. So that means over this line, the Newtonian potential, the gravitational Newtonian potential is constant. That's called geode. And that geode actually changes time to time for various reasons, like volcanic eruptions, which redistributes the mass, or similarly like some earthquake and so on, so on. This geode, or different other reasons, the geode changes. And it's very important to have a measure of that, because that defines how the Earth will be rotated or oriented, what are the changes in a very minute level. And that can be detected by very accurate optical clocks. So this is the same picture, what you see, a very small portion of that. Let's say you put a clock here on the sea level, you have a laboratory, like let's say IUCAA, and then you can put a small clock, like this miniaturized clock, what I was saying, or a clock which can be transported on top of the hills. Yeah. Then the tick rates of these two clocks will be different, even if all the other parameters are exactly identical. And why it will be different? Because of the gravitational shift, and that's how it changes. The change of Newtonian potential is function of capital G, the gravitational constant. Me and Re are the mass and radius of the Earth, and H is change of height. Yeah, so these clocks are at two different heights, different by quantity H. And if you put out the numbers, then it comes to be around 0.1 times H by 1 centimeter in a unit of meter square by second square. And now if you look into the fractional shift, delta F by F, which is equals to delta U by C square, and if you put delta U from these numbers and put all the numbers correctly, then you get delta F by F0, which is fractional accuracy, or change of fractional accuracy at different height, is 10 to the power minus 18 times H by 1 centimeter. H is the height. Yeah. So now if your H is on the, if your delta F over F0 is on the order of 10 to the power minus 16, which is achieved in a microwave, best microwave clocks. That means you can detect the change of age by about 100 centimeters, right? Just simple math. Wherever, if your delta F over F0 is 10 to the power minus 18, which is like optical clock. Optical clock has reached up to 10 to the power minus 19 today, but let's say 10 to the power minus 18 for the moment. Then you can determine change of Newtonian potential with an accuracy of 1 centimeter only. So you have a much better, 100 times better chance to determine any change of U, Newtonian potential, by change of any environmental things like volcanic eruptions and so on. And that's actually used. So this is from this paper, like they have derived the change of Newtonian potential which change due to the volcanic eruptions. And I mean, this way that I described you, they have determined with an accuracy of a few centimeters, and they determined also the right model. Using that, they determined the right models, that how the mass got distributed, and etc. So there is a wide scope of use for these optical clocks, for precision measurements to geodetic measurements and so on. So as I told you in the beginning of my talk, that now the next generation is actually connecting the optical clocks together and making a big collaboration so that we can enhance our sensitivity by several orders of magnitude. You can also try to find out different ways of making optical clocks. This is also being tried out, like now people are trying to make nuclear clocks. So looking into nuclear transitions, not in electronic transition of an atom, but nuclear transitions, which expected to give another 1 or 2 orders of magnitude more accurately. But probably it's better to connect different clocks around the world, so you have much better chance to detect any change or any of these things. It's the similar idea like why you want to have different LIGO detectors or gravitational wave detectors at different parts of the world. It's very much similar kind of idea. And here you see the red dots. These are actually the optical clocks, and in India we are creating in few places, including in IUCAA. And the ways they are connected by optical fiber communication, but not the simple optical fiber communication. Because here we are talking about precision experiment. In a simple optical fiber, the optical fiber length changes. It changes very small amount, but due to the change of the fiber length, the photons which are going from one end to the other end, they are coming out at different phases time to time because the length is not constant. So for this kind of measurement, if you want to make a connection, you have to stabilize this fiber, which is like 1,000 kilometers long or 2,000 kilometers long, to very accurately, like with an atomic level. Basically, you have to stabilize that, and that is actually a very non-trivial technique. But people have done that, and as you see here, example people have done not only through the surface but also under the sea. Like for example, University of Malta to University of Sicily. This is under the sea link, and they have stabilized it to a very accurate level. And here are a few examples throughout the world where this kind of ultra stable fiber link exists, from European Union Commission to USA and Italy and so on. Now I am coming to the last part of my talk, what we are going to do, what we are planning to do at IUCAA. So we are setting up a lab. The name of the lab is Precision and Quantum Measurement Lab. And the main aim of this lab is for quantum metrology and precision measurement, to do this kind of experiments what I just spoke to you. And also this will help to develop quantum enhanced technology to help our country for our quantum missions. As you know that DST this year has launched this quantum missions, and union budget 8,000 crore was allocated, which is of course due to this present situation may change. And the main goal of this mission, they have 4 verticals. One is quantum sensors and metrology, quantum computing and simulations, quantum communication, and quantum material and devices. By the way, this entire thing was, I mean, we are part of this thing. So it was developed all together by a big group. And what we are working, I am particularly working in the at IUCAA in the first vertical, that is quantum metrology. So this PQM lab will be focused on quantum metrology aspects. So what we'll do just quickly, like let's say basically you want to have this optical frequency comb, which, as I said, that it was Ted Hunch was getting Nobel Prize to invent that thing. But if you just take an optical frequency comb, this is not stable. I mean, the lines, so these are different spectral lines coming out of the optical frequency comb. They are discrete spectral lines, and they jump, they dance. They are not stable. So to stabilize these things, we have to have an optical clock which gives the absolute reference of an optical transition within very, very accurately. But still, this is not enough. We have to have the microwave clocks to fix this in between gap between two tips. This is in the microwave domain, about 80 to 100 megahertz, whereas the optical transitions are in a few hundreds of terahertz. And we need to develop this ultra stable Fabry-Pérot cavity for the, this gives short-term stability, whereas the optical clocks give the absolute reference. And also, like finally, once we do all this, we make these reference lasers, then we have to get this light to different parts for different kind of experiments or applications, and you need to stabilize this fiber, which are very long fiber. So there is a we need to develop this fiber stabilization technique also, like through two-way communications. It can be done. So these are different kind of parts that we have to work on. We plan to work on, and at this moment there are few places where clocks, atomic clock exists, but optical clock activity we are starting at Pune in IUCAA, and also ISAR is starting the strontium lattice clock activity. At Delhi, when I was there at NPL, optical clock activity we started, and maybe at some point all these clocks can be connected through optical fiber. At least in Pune, between ISAR and IUCAA, we are planning to do it in terms within this quantum mission project. This is only 5 kilometers. That could be very good test bed before going to the continent, let's say national level. It could be a very good test bed for that. And they are at ISAR Pune, they are developing the strontium lattice clock, and we are developing the ytterbium ion clock. As I described, these two clocks could be a very good measure for the fundamental science experiments, as I have already described these things. Okay, so that's our basically goal, and that brought me to my conclusion. So the optical clock is not only for time and frequency metrology, but it can do much better thing. In fact, optical clocks are used for studying fundamental science, and that we have to do it. It also supports different kind of very state-of-the-art experiments, like let's say quantum communication, or in fact also LIGO. So it's very important to develop good kind of clock and the advanced technologies to connect them together. And what we plan for, particularly at IUCAA, like developing this kind of reference clocks or optical clocks to support the quantum missions, developing this kind of very ultra stable link between, at least between ISAR and IUCAA to start with, and also in far future developing this kind of chip trap so that it can be made miniaturized and make it transportable. So thanks for your attention.
Thank you very much, Subhadeep. Great talk, and we're running a little short of time. I'm sure people have a lot of questions. If you have a question, can you please raise your hand in the participants window? Okay, I'm starting with Shwanjit Mitra. Unmute.
My question is that when you are trying to build this worldwide network of clocks, there are so many uncertainties which you have already mentioned, which are transients like volcano and maybe some tides, etc. All those things are going on. So the change in gravitational potential is always also changing the clocks, right? I mean, it is very small, but the precision you want to reach, there it matters. So how do you take that into account?
Yeah, that's actually a very good point. And that's why, if you remember, I said the link, the fiber link between two different places has to be stabilized. So what you care about is length of the fiber between two clocks. Let's say you have two reference clocks in two places, and due to this, any perturbations, gravitational waves or anything, what can change is actually this fiber length of the fiber. So it's very important to stabilize this length of the fiber, which is a state-of-the-art technology. So until and unless you do that, two clocks cannot be compared. So you are absolutely right. So that is one of the key technologies that one has to develop. And that is, I mean, developed countries, they have already done it. But in India, it doesn't exist at this moment. We have to do it.
Okay, thanks. Ravi from IAA, can you ask your question? Are you able to switch on your audio? He sent a question by chat, but I'm unmuting you. You can ask your question.
Okay,
thanks. Please ask your question.
So I just put the question. Subhadeep, thanks for this very interesting and exciting talk. And so one thing you said that different labs all over the world now try to share these frequency and time standards, and they are able to do it on some kind of network. And you also talked about the laser frequency comb, which is finding several applications in astronomy, including the spectroscopies and the search for this change in fundamental constants. So one problem with LFC is that the technology is still very complex, expensive, and it's not kind of straightforward to set up the whole thing at the observatories, right? So my question was whether it is possible to distribute a wide band laser frequency comb signal over a long distance from some kind of central lab, and then whosoever wants can make use of it. So was such a thing being attempted somewhere, or is there a possibility of such a thing?
Yeah, absolutely. So this is what you see. This is absolutely possible, but it's not straightforward, as you already realized. And the main reason is, like, we are talking about transmitting photons, keeping their phase as it is, keeping their phase information as it is. So transmitting photon is very easy. I mean, optical fiber communication, they do it regularly. So what we have to do, we have to use the same fiber. We have to go to the optical communication wavelength, 1550 nanometer. But that wavelength first has to be stabilized with respect to a reference laser. And this reference laser is basically this entire system, this clock and etc. what I say. And then this 1550 nanometer light or photons will go through the fiber. That fiber length has to be stabilized. So that is, of course, possible. And as a test bed, we want to first try it between ISAR and IUCAA. This is about 5 kilometers. In fact, before that, there is one more step. We have to try it within the lab. Within the lab, we will use a fiber spool of 100 kilometers, let's say, etc. Then we'll try to develop the techniques to stabilize the fiber length. But this is quite a bit different compared to putting the fibers actually under the ground, even for a few kilometers, because actually under the ground, you have a lot of vibrations, moving cars, moving trams, etc., etc. So after this first step, we'll go for this IUCAA to ISAR thing. And then once this technology is developed, or we are certain that we can do it, then it can be taken to a national level project, which is, of course, beyond our limit. I mean, it has to be done by NIC, or somebody like that. But that's certainly possible. I mean, other countries, European Union have done it over thousands of kilometers. Japan have done it. China has done it.
Great. Are there any more questions? Please raise your hand or in the chat. I don't see any questions in the YouTube feed. There aren't any there. If there are any other questions, otherwise, oh, there is one more. Okay, I think we have just about time for one more. Avinav Dhawan. I have unmuted you. Go ahead. Yes. Go ahead. You are unmuted. Avinav, you can ask your question.
I don't hear.
Well, the microphone is unmuted. Go ahead. Can you hear me? Okay, we'll go on to Indulekha now. Indulekha has a question. Indulekha has a question. This might be the last question.
It's a naive question. When you are putting clocks on the surface of the Earth network, the ISS, etc., are we making an assumption that we know exactly general theory of general relativistic time dilation effects exactly, so that we can make an estimate for delta alpha by alpha?
Sorry, your voice was breaking a little bit. So you are saying that whether we know about the
general relativistic time dilation, do you know them exactly?
So okay, so yes, so actually we don't know that. We want to measure that. That is, the atomic clocks are used to measure that what is the change of clock frequency shift due to change of U, the potential. So clocks are actually used to measure that thing. So maybe that theory can be tested by the actual measurements. That's probably the goal. Or the other way around, once you know that those changes, then you can incorporate that and you can go to the further level, let's say measuring the Lorentz violation and etc. etc. It's actually like a ongoing thing. I mean, you can't really say that I know exactly these things and then I am deriving that. It just goes together. You do some measurement, you change your model. Typically, what happens in everything inside.
Bootstrap. Okay, great. Thank you very much. I think we've run out of time, but thank you very much, Subhadeep, for a wonderful talk, and thank you all the audience. I mean, you can show your reaction by applauding on on Zoom, and we'll see you next Thursday.